Hello and welcome back. We're going to be going over 3.6, predicting precipitation. We're now dealing into our quantitative analysis of solubility and dissociation. So before we go any further, just a little bit of review when dealing with dilution. So we're dealing with concentration still. Remember, concentration is the amount of something in a given volume. So our molarity, or our molar concentration, is moles over volume in liters. So when we're diluting something, we are just changing our volume. So our amount of substance doesn't change, meaning that our moles that we initially had is the same as the moles that we ended up with, or our final amount of moles. So I can rearrange these equations now, and you may recognize this from last year. I'll change these i's to 1s and f's to 2s. You can keep it as i's or 1s or f's or 2s. It doesn't matter. But our molarity that we started with and our volume we started with, just rearranging this because moles is molarity times volume, must be then equal to our final molarity and our final volume. So when something has been diluted, usually we know our initial concentration and volume, we know how much we've been diluted by, so we can find our final volume, and then we'll just rearrange this, and our final concentration is always going to be equal to our initial amount of moles, so our molarity and volume to start with, divided by our new volume. So this is not the amount that we've added to our solution, but the total amount of solution once we're finished our dilution. So make sure you are comfortable with this terminology and you review your dilution formula. So let's just do an example of a dilution. This is taken straight from a question you would have seen last year in your solutions unit. So let's say I have a volume of 200 milliliters of 0.6 molar concentration of iron 3 chloride. And that solution is going to be mixed together with 100 milliliters of 0.8 barium nitrate. No precipitate is formed, meaning that the entire amount here has all been dissociated. So this just tells me that all this 0.6 molar concentration of iron chloride has completely gone into the ions. I have no precipitate in solution. So step 1 is just to balance my dissociated equations, and I've actually done this already, to determine the initial ion concentration. So here I'm going to do this and find what my ion concentrations would have been in their initial solution before I combine them together. So in my iron chloride here, I had 0.6 molar. So 1 to 1, this is still 0.6 molar of my iron, but I have 3 chloride ions. So I'm going to multiply this amount by 3 to find that my chloride concentration is 1.8. And that will be actually two decimal places here. I'm sorry, 2 sig figs. What am I doing? There we go. I'll do the same for my barium nitrate. I started with 0.8, so 1 to 1 here, so also 0.8, but then I'm going to multiply this amount by 2. For the 2 sig figs, that is 1.6 for my nitrate concentration. Now, I've done this before I've diluted everything. You can decide you want to find your diluted concentration first, as long as my dilution formula is somewhere in here, and I'm actually going to do my dilution in my next step. The one thing I'm missing here, I know my initial volumes, so this was 200 milliliters, and this one was 100 milliliters. I know my initial concentrations, but I need to calculate my V2, my final. So because I'm adding these together, my total amount of volume, this would be my 200 milliliters plus my 100 milliliters to give me a total volume in my new solution now of 300 milliliters. And I can change this to liters, but as you see in my formula below, because I have milliliters on both sides of my equations, it's actually just going to cancel each other out. So I could change them both to liters or keep them both in milliliters, sorry. It doesn't matter here, just because I will be canceling out my units either way. So now that I have my initial concentration, initial volume, and final volume, I am ready to use this formula up here to find what my new concentration is going to be of these ions after this dilution has occurred. So I have 4 ions in solution. I'm going to do this 4 times. I'm trying to find what the ions are for each ion. Now, be careful here. If I had, say, this was barium chloride instead, then I'd have to add all my chloride together. But I have 4 separate ions, so it's all good to do this separately. So for my concentration of my iron, I started with 0.6 in a 200 milliliter solution, and I'll divide it by my total volume. See how this is also milliliters, so those cancel out. And I find that my final concentration after dilution was 0.4. I'm going to do this again for my chloride. So this time I'm using the 1.8. I still had initially 200 milliliters. You'll notice your total volume, because everything's been combined together, is always going to be the same for all these ion concentrations. So I have 1.2 molar concentration after my dilution of chloride ions. You should also just double check that your math makes sense. If I have added volume, right, I'm adding some volume here. My volume is increasing. I should expect that my molarity, my concentration, goes down. So if I started with 0.6 and I added more volume, it makes sense that it's gone to 0.4. If you find that you started with a lower number and end up with a higher number, you should recognize that something's gone wrong. Adding volume lowers our concentration. So let's continue with barium and nitrate here. So with barium, we had 0.8, and now it was a 100 milliliter solution that we started with there, but our final was still 300. So we have 0.27 molar concentration of our barium. And then for my nitrate, where were we here? 1.6. Still in that 100 milliliters to start with, but we diluted it to 300. So we get 0.53 molar concentration of nitrate. So that's how you would do any sort of dilution problems. Make sure you keep in mind, if you are ever combining 2 solutions, or there's any scenario that you read where a volume has changed, you need to make sure you take that into account when trying to calculate the new concentration. Concentration is not going to stay the same if solutions have been added together, meaning our volumes have changed. There's also another note here. Remember that if equal volumes are mixed together, so maybe I didn't tell you what my initial volumes were, but that they were equal, therefore you've doubled the volume, then you don't explicitly need to write out your dilution formula. Just know that your final concentrations will be 1/2 of the initial ones. Let me just do a little proof here for that. So equal volumes added together, well, this means that my final volume is just 2 times my initial. No matter what, if they're equal, it's always going to be 2 times this amount. So knowing this, if I go back to my M1V1 equals M2V2, I rearrange this to solve for my final concentration, so M1V1 equals V2. Plug in the fact that this is just double my initial. I can cancel out my initial volume, and what I am left with is that my final concentration is just my initial concentration divided by 2. So remembering this is going to save you a little bit of time, save you some room doing the calculations. If you don't remember this and had to do it out by hand, don't worry, you will still get the correct amount. Although if you were told equal volumes, you won't know what to put here. You could arbitrarily put 1, and then therefore 1 and 1 would give you 2. So try to remember this here. Okay, now can we apply this going back to what we've been talking about so far in terms of our solubility products, so our KSP and dissociation and solubility. So remember back to this initial table here. Remember, this is a qualitative analysis. This is how we can qualitatively predict if we will have a precipitate or not. However, this chart is not always going to be correct because it depends on our specific concentrations. For example, remember that this has arbitrarily said we've decided that solubility here means that it can dissolve more than 0.1 moles per liter at 25 degrees Celsius. So it doesn't mean that no matter what concentration I have, I'll always have either precipitate or be soluble. I can have something with low solubility, and it can still all dissolve without forming a precipitate if I have less than this 0.1 moles per liter. So it don't quite follow these guidelines when doing quantitative analysis. We're going to have to use our KSP and our concentrations to figure out whether or not it actually dissociates fully or not. So we have a scenario here. We're looking at 2 solutions being combined together, our calcium nitrate and our sodium sulfate. So is a precipitate going to occur, is it not? Well, if we were to look at our qualitative analysis, so doing a double replacement, replacing these, switching these 2 metals, we would know that our products are going to be sodium nitrate. We'll write this down. And calcium sulfate, just to the side. So according to our data package, if we're looking at qualitative analysis, well, our sodium nitrate, both are always soluble in solution, so we don't need to worry about that. But for calcium sulfate, according to this chart, it should have low solubility, so it should form a precipitate. So we're going to, let's say, pretend to do this experiment in a laboratory setting and see what our 2 results here are. So 2 experiments. We have our first one and our second one. So we have equal volumes of 0.002 molar calcium nitrate and sodium sulfate, and they're going to be mixed. So we would anticipate a precipitate to occur based on our chart because we know that calcium sulfate has low solubility. However, we notice that when we mix these 2 with these initial concentrations, no precipitate occurs. In case 2, now we have a larger concentration of both at equal volumes. These are mixed together, and then just like predicted, a precipitate is observed. So how can it be that we can mix the same 2 exact solutions together, and in one case it forms a precipitate, but the other doesn't? Well, it has to do with the concentration that we initially started with. So if a precipitate would occur, this would be our equilibrium reaction, our equilibrium expression here. So our value of KSP can dictate exactly how concentrated the products must be in order to form a saturated solution. So we can actually use our KSP here to see whether we are at a saturated solution or not. A precipitate is only going to occur, so this equilibrium is only going to shift left when our system is super saturated. That means that we have too much products, too much ions have been dissociated in solution, so we're going to shift to the left to counteract the stress, and a shift to the left means that we will produce more reactant, which is our solid. So we're going to see a precipitate occur. And this is going to happen because shifting to the left is then going to reduce the ion concentration of our products here. So supersaturated means we have too much products. It's going to shift the solution or the equilibrium expression to the left here. So this is when we would see a product. So, or precipitate. So it's possible that in this first case, we had no precipitate because we had not reached a supersaturated solution yet. So to figure out kind of which way it shifted, whether our system is favoring the left side, meaning it is so far unsaturated, equilibrium, so it is saturated, equilibrium is on this side, or supersaturated on the right, we can use what's called a trial KSP. So just like we had our trial KEQ, meaning whether it's going to shift to the right or the left or be at equilibrium, we can also use our trial KSP. So if our system is much to the left, it means that it is unsaturated, that we can continue to dissolve, continue to make more product. If our equilibrium is to the right, it means that we are supersaturated. So we have too much product, and in turn, it's going to continue to shift to the left, making a precipitate at a solution. So let's look at both the cases and figure out why or why not a precipitate did occur. Now, our KSP can be obtained from our data booklet. So we're looking for our calcium sulfate here. It is in alphabetical order. It is 7.1 times 10 to the negative 5. So this is my known KSP when I have a saturated solution. So that means at equilibrium. This is my constant. So we're going to keep this in mind when we're dealing with our trial KSPs based on the conditions that we were given in our experiment. So case 1, remember this was the one that did not form a precipitate. So I have equal volumes of 0.002 calcium nitrate and sodium sulfate. So this is the concentration of both of these solutions. And they are at equal volumes. So it means that when I mix them together, all my ion concentrations are actually going to be diluted by half, right? Because these are equal volumes. So this is taking into account my dilution equation. So that means my calcium, which, and I'll show you how I'm getting these values. So let's take a step back. My nitrate, so in my double replacement, I would have calcium nitrate, which would give me calcium and nitrate, my sodium sulfate in solution, which would give me my sodium and my sulfate. And then for my precipitation reaction, I would have my calcium sulfate that is associating into calcium and sulfate ions. So my calcium was coming from my calcium nitrate, which was 0.002. I'm going to half that for my dilution, so 0.001. My sulfate, which was coming from my sodium sulfate, was 0.002 as well. I'm going to half that to deal with my concentration being diluted. So they're both the same here, but recognize where I am getting these initial concentrations from. It's from their initial amounts. So knowing this, then my trial KSP is going to be my two ions multiplied together. So 0.001, 0.001. So I have 1.0 times 10 to the negative 6. So I am going to be comparing, this is my trial, to my actual. So I'm comparing 1.0 times 10 to the negative 6 to 7.1 times 10 to the negative 5. So here my trial is less than my actual. I have one more decimal place in my trial than my actual here. So this means that I do not have enough products, meaning my solution is not yet saturated, it is unsaturated, and no precipitate will form. So my trial is less than the actual. So in order to reach the actual, it is going to continue to shift to the right, meaning that it's going to continue to dissolve more ions in solution until it reaches a saturated solution. So this is why I had no precipitate in here, because we have not yet reached our saturated solution, so we couldn't have become oversaturated and shifted to the left to form a precipitate. So when my trial is less than the actual, no precipitate will occur. Let's look at case 2. So this time I had a higher concentration, equal volumes again, so I'm simply going to be taking these and dividing them by 2. So this time I'll have 0.01 molar concentration of my calcium ions, 0.01 concentration of my sulfate ions. So my trial KSP is now these multiplied together. So I get 1.0 times 10 to the negative 4. So this time, if I'm going to compare that to my 7.1 times 10 to the negative 5, my trial here is more than my actual KSP. So my trial is greater than the actual, which means I am going to have to shift to the left because I have too much products here. My solution is what's called supersaturated. So I have too much of my products. It's now going to shift to the left in order to go back to a saturated solution. Since it's shifting to the left here, that means I'm going to be forming some of this solid calcium sulfate. So that is why we'd see a precipitate here. So understand these two conditions, what it means when our trial KSP is less than the actual amount. So no precipitate will form, it will continue to dissolve. And if our trial KSP is more than the actual, meaning it will have to shift left since it is supersaturated and will form a precipitate. If it is equal, it is completely a saturated solution, so also no precipitate will have occurred, but it is the maximum amount that can dissolve. We are to true equilibrium. So there are a lot of questions, but try all these questions dealing with trial KSP, whether or not a precipitate will occur, and then using your KSP expression to find some concentration as well. All right, that's all for now.